This is another application for power series. It's actually the generalization of them. And well, we're going to use this Taylor and Maclaurin series to obtain power series for other elementary functions. Like, well, last time we were working on the the generalized geometric series for a power series, not for a series of integers, like back in section, what was that, 11 or 11.2 or so, 11.3. So, well, we got power series for the natural log of 1 plus x function, the power series for 1 over 1 minus x, have power series for the arctangent function. So, well, again, power series represent elementary functions, so it should be natural that other functions like the a to the x function, the natural exponential function, what else, sine and cosine, also must have a power series representation. However, none of those functions, e to the x, sine or cosine, can be derived from the function 1 over 1 minus x, because neither their derivatives nor their integrals are related to such a rational function. So in this case, we're going to use Taylor and Maclaurin series. But number one, let's do a brief review of what you guys did back in Calculus 1. So in Calculus 1, you did something called linear approximation, and well, so essentially, linear approximation is finding the equation of the tangent line at a given point. However, we further use this linear approximation to approximate the values of some weird numbers without the use of the calculator. Well, so let's look at one example of something you did back in Calculus 1. So find a linear approximation for the function f of x, the square root of x at x equals 25, and then use it to approximate the value of 26.5. Well, so there's two elements that we need to, in order to come up with a linearization. Number one, the slope and the point. So we already have the part of the point. However, we're just given the x value. We would need to find the y value by plugging in the x value in the original function, which happens to be 5. So the point will be 25, 5. So that's the point at which we will find the equation of the tangent line. So we need the slope, and to get the slope we need to find the derivative. However, we need to rewrite f of x equals x to the 1/2. We cannot differentiate the square root of x just as is. So the derivative, that's going to be 1/2 x to the negative 1/2. And let's rewrite it in a nice way that we can evaluate the 25, because like this with negative exponents, I don't think it's a good idea. So f prime of x equals 1 over 2 root of x. Okay, so that's after simplifying. And to find the slope is found by evaluating the derivative at the x value of the point of tangency, which is 25, 1 over 2 root of 25, and that's 1 over 2 times 5, which is 1/10. So that's the value of the slope. Okay, 1/10. And well, over here we can already find the equation of the tangent line by using the point slope form. Y minus y1 equals m times x minus x1, where y1 is our 5, the slope, which is 1/10, and that's x minus 25. Alright, and let's solve for y. That's going to be y equals 1/10 x minus 25 plus 5. And I know what you might be thinking of, distributing the 1/10 over the two terms x and minus 25 inside of the parentheses. But my advice is not to do that, because if you leave it like this, that's going to give us that's going to make the problem a lot easier when simplifying the calculation. All right, well, so this means, what does that mean? This means that the square root of x is approximately 1/10 x minus 25 plus 5 at the point 25, comma 5. So that's the linear approximation, and in this situation we need to specify the point at which the approximation is accurate at, you know, and in this case it's this point right here. Alright, so now we can evaluate 26.5. We can use this approximation to evaluate the square root of 26.5. That's going to be approximately, well, that's a 1/10. 26.5 minus 25 plus 5. Well, let me change colors here. So 26.5, 26.5. So instead of evaluating the square root directly, we're going to use this linear approximation to estimate that value. And well, that's going to be approximately, so 26.5 minus 25, well, that's 1/10, 1.5 plus 5, which is, well, that 1.5 is 3/2 plus 5, which is approximately, that's a 20 in the denominator, 3. Then we multiply by 20, divide by 20. So that's 20 times 5, that's 100, 103 over 20. So that's 103 over 20. And so that's the approximation about for 26.5. Well, what did we do? I mean, why do we review this here? But what's the bigger picture anyway? So we have the graph of square root of x, and we found the point of tangency at 25. So let me scale 1, 2, 3, 4, 5. So that's 5, 10, 15, 20, 25, 30. So we found the point of tangency, the equation of the tangent line. And well, notice how at a few points around 25, the actual value, which is the value on the graph of the square root of x, it's pretty close, if not the same, as the one in the linear approximation. So for example, we could use this approximation to maybe still approximate the square root of, I don't know, maybe 22.3, for example, or the square root, well, maybe not 20, maybe not that low. Well, we got the square root of 26.3 in this case, right? I don't know, 0.5. But well, the question is, can we use this linear approximation to evaluate, say, the square root of 7.3, for example? And the question is no, because see the difference here? I mean, the answer is no, because see the difference between the actual value and the approximated value. So there will be a huge difference. Yeah, this, even though the graph shows like a tiny difference, it's because of the scale. Well, it's a big difference. So in this case, we have a couple of options. Number one, or we create a new linear approximation that is at another center value, that preferably at an easy number that has a perfect square and that it's close to 7.3, which in this case would be 9. We would do all this process. So that's one way. Or another way to go beyond the linear approximation, and that's what we're going to do in this in this section. So we're gonna go from the linear approximation to the quadratic, the cubic, well, depending on whatever they're asking us for, and then so that's going to take us to power series, and we're going to express this in sigma notation. And of course, some of the applications for this are going to be evaluating this kind of values. All right. So Taylor and Maclaurin series. Well, so I mean, check the power series. Looks a lot similar to what we have done before, but except that this series right here has this Fn, which is the end derivative divided by n factorial, and it's evaluated at A, the center. So that's for the Taylor series. However, for the Maclaurin series, well, there's a little typo here, actually. For Taylor series, which is a series centered at 0, that's x to the n, simply, not x minus a. So we're going to take a few derivatives, so not just the first derivative like we did for the linear approximation. So for the linear approximation, we found the first derivative. To get the slope for the second derivative, we need to take not for the second derivative, for the quadratic approximation, we need a second derivative and evaluate it at that center value. For the cubic approximation, we need a third derivative and evaluate it at that center value. Well, the formula right here looks big and looks just very symbolic. So how about we do some exercises. All right. Use the Maclaurin series to express a series expansion to find a power series for the function f of x equal to 1 over 1 minus x. In fact, this is the series that we used last time. For this, we got sigma n equals 0 to infinity of x to the n. This is the generalized geometric series. However, this time we are going to obtain this series using Taylor series expansion. So, all right, just want to warn you about this. These exercises are going to take a while because we're going to take a few derivatives, we're going to do some evaluations, and we're going to write a good number of terms. So, okay, so we're going to evaluate this at. So Maclaurin series means centered at 0. Okay, so f of x, which is 1 over 1 minus x, and I'm going to rewrite this 1 over 1 minus x as 1 minus x to the negative 1 because we're going to take the derivative later. In the meantime, we're going to evaluate f of 0, that's 1 over 1 minus 0, which is 1. Take the derivative. Taking the derivative, so negative 1 times 1 minus x to the negative 2, and rewrite it as negative 1 over 1 minus x quantity squared. Evaluate the first derivative at 0, so that's a negative 1 over 1 minus 0 quantity squared, and that's a negative 1. And then f double prime, that's positive 2 times 1 minus x to the negative 3, and that's a 2 over 1 minus x to the third power. Well, actually this is positive. And the second derivative, evaluated at 0, that's a 2 over 1 minus 0 cubed, which is 2. And let's do one more. So typically we go up to the third derivative or the fourth derivative depending on the needs. So that's the third derivative, and that's a negative 6, 1 minus x to the negative fourth power, and that's a 2 over, or actually no, not 2, it's actually a negative 6 over 1 minus x to the fourth power, and evaluating this third derivative at 0, that's going to give us negative 6 over 1 minus 0 to the fourth, which is negative 6. Alright, these coefficients right here, let me highlight them first. These coefficients are the Taylor or Maclaurin coefficient, well, depending on the expansion that we're working on. If it's Taylor, well, these are Taylor coefficients, but because this is a what you call a Maclaurin expansion. This will be Maclaurin coefficients. What are these coefficients? So number one, let me write down the whole formula first so you can see what they are. So this function f of x, we're going to turn it into a sigma expansion, n equals 0 to infinity, and that's the nth derivative evaluated at 0 because that's our center, over n factorial x to the n, and in this case expanding a few terms. So I'm going to expand up to, well, in this case, the 4 terms actually. I'm going to start with f of 0 divided by 0 factorial plus f prime at 0 divided by 1 factorial. That's x to the first power plus, well, technically this is x to the 0 power. I'm going to write it. And f double prime at 0 over 2 factorial x squared plus f triple prime evaluated at 0 over 3 factorial and plus. This one just goes on forever. Alright? So, let's see. Well, actually, I think I did a few sign mistakes. Did I? Yes. This one, actually, all of them are supposed to be positives, not negatives. I didn't take into account the mini chain rule here. And let me just fix this real quick. I'm just going to put plus signs to indicate that they're all positives. Okay? So, well, okay. This one right here is this first coefficient, Maclaurin coefficient. This plus 1, it's this coefficient here. These two, it's this coefficient, and that third coefficient will be this one right here. And I also need an x to the third power. Alright? And then it would be the fourth derivative, x times x to the 4 over 4 factorial, the fifth derivative, x to the 5th power over 5 factorial, etc. But I mean, let's just write a few and then distinguish a pattern here. So let's substitute what we have. So this will be f of x equals to f, the function evaluated at 0, which is 1, x to the 0 over 0 factorial, plus f prime evaluated at 0, that's 1, x to the first over 1 factorial, plus f double prime, which is 2, x squared over 2 factorial, plus 6 x cubed over 3 factorial, plus dot dot dot. Okay? And, well, in this case, let's simplify f of x as a polynomial. Well, 1 times x to the 0 is just going to be 1 over 0 factorial, which is just 1. That's going to be 1. And this is just x. And 2 factorial, which is 2. These two cancel out. That's x squared. And 3 factorial, which is 6, they also cancel out. Plus x cubed. And, well, this goes on forever. And, well, if you look at the pattern here, sigma n equals 0 to infinity, x to the n power, which is the same series that we obtained using the geometric series. However, this time we're doing it in a different way. We're doing it in a more generalized way using Taylor series or Maclaurin series, which is actually the series that generates pretty much a power series for every single elementary function. Alright, so we do this just so you can see the connection between the two series, how they can obtain from different methods. Now let's have a look at another example. So let's see, they're asking us to find a Maclaurin series expansion for f of x e to the x. So finally we're going to get that power series. So, well, they're not telling us the center at which they're asking us to find the series. However, they're telling us Maclaurin. Because they're telling us Maclaurin, this means centered. At 0. Otherwise, well, they would say find a Taylor series centered at a particular value. So let's do the same process. Evaluate the original function at 0 and some of its derivatives. Well, so f of x, which is e to the x, and evaluate the function at 0, that's e to the 0, which is 1. Take the derivative, f of x, that's also e to the x. Evaluate f prime at 0, that's e to the 0, which equals to 1. F double prime, it's also e to the x. F double prime at 0, that's e to the 0, which is 1. And let's do one more derivative. I know it's the same thing all over. However, when we have a coefficient in front of x, which we will do, we will do later, that's going to be, well, you'll see what's going to happen there. So evaluate all this at 0. So the coefficient is 1 for all of them. All right. So there's really not that much interesting here. Well, so in this case, let's write the formula again. Sigma n equals 0 to infinity fn evaluated at 0 over n factorial x to the n. And well, let's start expanding f of 0 over 0 factorial x to the 0. Just write down the pattern. F prime at 0 over 1 factorial x to the first, f double prime at 0 over 2 factorial x squared, f triple prime at 0 over 3 factorial x cubed. But well, we don't need to find more terms beyond the third derivative. 3 is usually fine. Well, the homework may ask you to fill in the blanks on WebAssign for a certain number of terms. So try not to get everything in your head straight to the final answer, because some problems are like set up first and then simplify. Alright, so well, all these coefficients right here, I'm going to highlight them using one single color this time. So this coefficient, this is a 1. This is also a 1 over here. This is another 1 here. This is another 1 here. And that's going to be f of x equals 1 over 1 factorial x to the 0 plus 1 over 2 factorial x to the first power. Wait, no, that's a 0 factorial. And that's a 1 factorial. And plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus dot dot dot. Well, my advice is not to simplify the factorials when it comes to getting the series in sigma notation, because if you compute 0 factorial, which is 1, and then another 1, and then a 2, and then a 6, it's not going to be easy to find a pattern trying to find like an arithmetic or another kind of sequence. So just leave it in terms of factorials. And this is sigma n equals 0 to infinity. What do we have? X to the n. And we have the pattern of factorials of the integers. And that's the series expansion for the exponential function. All right, let's make a connection with this particular example to what we did at the beginning of this section. So number 1, okay, let me keep simplifying this. This time I'm going to simplify, so that's 1 plus x plus 1/2 x plus x squared rather plus 1/6 x cubed. All right. So over here, what do we have in this final answer? In this final answer, we have a few things. We have number 1, the linear approximation, the quadratic approximation, and the cubic approximation, and we could potentially have the quartic approximation, the quintic approximation, etc. Now, what do these approximations do with relating this with the original function? So we have a few graphs at the bottom of this page. So in this case, here we have the linear approximation. Linear, and then what do we have? We have the graph of the original function e to the x and its linear approximation centered at 0. So if we use the linear approximation, we could use it to evaluate, well, check this range of values that I am highlighting here. So this is a decent range of values that we can evaluate using the linear approximation, because if I go all the way here, for example, check the difference between the approximated value and the actual value. So we cannot use a linear approximation to evaluate values for beyond 0, too far away from 0. So number one, if I wanted to evaluate something like e to the 1.3, for example, 1.3, well, I would need to find another linear approximation near 1, and in this case, since that is closer to that new center, well, we can use that. However, that's one solution, create a whole new linear approximation, or the other solution is come up with a quadratic approximation, for example. And check how the quadratic approximation, it's giving us a wider range of values for which we can use that approximation. In fact, if you notice, so the graph in blue, which is the quadratic, so the quadratic approximation overlaps the original function e to the x at more points than the linear does, compared with the linear approximation. So check how many points it overlaps. Not that many. Go to the cubic approximation. The cubic approximation is giving us even a better approximation. It's a wider range of values. And by the time we go to the quartic approximation, check how many values will the approximation overlap with the original function. So in this case, instead of finding a new linear approximation at another value, for example, if I wanted to evaluate at -1, we can use the quartic approximation instead of creating a whole new linear approximation at -1, for example. So that's why we add more terms to the polynomial approximation. So that's why we go beyond the linear approximation to have more accurate results. And well, how accurate will those results be? Well, that depends on the number of terms that we add to the Taylor series or Taylor or Maclaurin series. For example, if this were a radical function, well, now we can use that quartic approximation to maybe, if it's centered at 25, we may now use it to calculate a value of, I don't know, the square root of 63.4, for example, because that's now overlapping more terms, or rather at more points on the original function. So that's a new result we obtained. A power series for the exponential function. In the end, we're gonna do a summary of all these series expansions. In the meantime, let's look at a few more examples. The sine function. Find a Maclaurin series expansion for sine x. And well, Maclaurin means the series is centered at 0, and we're going to go up to a few derivatives. Well, you'll see what happens with the sine function. So, f of x, which is sine x, evaluated at 0, that's sine 0, and that's a 0. Find the derivative, that's cosine x. Evaluate the derivative at 0, that's cosine 0. And cosine of 0 equals to 1. Take the second derivative, the derivative of cosine, which is negative sine, and find the second derivative at 0, that's a negative sine of 0, which is 0. Find the third derivative, and that's negative cosine x. Evaluate the third derivative at 0, and negative cosine of 0 equals to negative 1, because cosine of 0 is 1. 1 times that negative in the front, that should be a negative 1. And well, let me do one more derivative so you can see the pattern here. Because notice some of the coefficients are 0. That means that some of the terms are not going to appear in our polynomial expansion, as you will see. So that's the fourth derivative. And well, for the fourth derivative, we use a special symbol. So we don't write four like commas in this case. We write it from the fourth derivative and beyond. We write the number in parentheses to indicate, in this case, the fourth derivative. And that's the derivative of negative cosine. That's going to be, well, number one, the derivative of cosine is negative sine times the negative in the front, that's a sine x. And that's f, the fourth derivative, or the quadruple prime. So that's a sine of 0. But check this out. That's going to take us back to the same of the original function. If I take the fifth derivative is exactly the same as the first derivative. The sixth derivative will be exactly the same as the second derivative, and the seventh one will be exactly as the third, and so on and so forth. That's because, well, see how the sine and cosine function oscillate between negative 1, 0, 1, 0, negative 1. So that happens with their derivatives. And well, so let's write down the power series. So f of x equals sigma n equals 0 to infinity, and f sub n of 0 over n factorial. And again, that's the f of 0 over 0 factorial, x to the 0 plus f prime of 0 over 1 factorial plus x to the first, f double prime at 0 over 2 factorial, x squared. Well, you see the pattern here, right? That goes on forever. Just the order of the derivative keeps increasing, the factorial in the denominator also keeps increasing, and so the powers of x keep increasing in this case. So let's evaluate using these coefficients here. Let me highlight them. So all we do right here of finding these derivatives and evaluate them at the center value is to find these coefficients here. Everything else is straightforward from the notation. Just write down the corresponding number, 0, 1, and 2. All right. So something fun is going to happen here. And well, f of x equals, so the first term is 0. That means 0 x to the 0 over 0 factorial plus 1 x to the first over 1 factorial plus 0 x to the second power over 2 factorial plus, what would be next? Negative 1 x to the third power over 3 factorial. And well, the next one would be plus 0 x to the fourth power over 4 factorial. Well, that's going to be 0. And well, the next coefficient would be, because this 0 is the same as this 0, it would be a positive 1 plus 1 x to the fifth over 5 factorial plus 0 x to the 6th over 6 factorial plus negative 1 x to the 7th over 7 factorial. So the pattern just continues in here. You see 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. That just repeats. It's the same pattern repeats here. 0, 1, 0, negative 1. 0, 1, 0, negative 1. That's the pattern that just repeats periodically here. And well, of course, some of the terms are going to get simplified, or zeroed out. That's 0, 0, 0, and 0. So what are we going to be left with? So we're going to be left with f of x equals to, well, I'm gonna leave this x over 1 factorial. I know 1 factorial is 1, but I need this factorial symbol to find the pattern and write this using sigma notation. And then that's going to be minus x cubed over 3 factorial, and then plus x to the 5th over 5 factorial, and then the next one would be negative x to the 7 over 7 factorial. And well, this pattern goes on forever, of course. Now our task is to find or to represent this polynomial function, this polynomial approximation, using sigma notation to express this as a power series. So there's a couple of things that we need to observe. So number one, we have an alternating series, and it alternates between starting at positive, then negative, then positive, then negative. So that's going to be negative 1 to some power. Let's see if negative 1 to the n power works. Well, negative 1 to the 0 power, that's going to give us a positive 1. For n equals 1, negative 1 to the first power, yes. Well, or actually to, no, yeah, that's for sure going to work, all right? And well, what else? What are we going to have? Well, powers of x. X to what power over what? Okay, let's observe the power. So we have x and x to the first power. Let me write down that invisible 1. So x to the first power, x to the third power, x to the 5th, x to the 7. So do you notice a pattern here? What are these numbers here? Let's see if n plus 1 works. N plus 1. So for n equals 0, that's going to be 0 plus 1. Well, it works for the first. N equals 1, that's going to be 1 plus 1. Well, that's going to give us a 2. So we need a 3 here. So how can we fix that power here? We're getting close, actually. Yes. 2n plus 1. So that's the definition of the sequence of odd numbers, right? That's the form of odd numbers. And we have the same pattern in the denominator, 2n plus 1, and turn it into a factorial. And that's the power series representation for the sine function. And well, if you do the ratio test on this function, you will find out that this will converge for all real numbers. And so the exponential one, I think we did the example for the exponential in the previous, but I didn't tell you it was actually the exponential function. Now, one thing to notice here and to make connections, what do we notice here? Well, so odd powers and odd factorials. That's because f of x equals sine is an odd function. So that property gets reflected even in the terms or the pattern for its power series representation. Alright, so let's see, what do we have next? The next one is going to be pretty quick, actually. Find a Maclaurin series expansion for cosine x. Well, so in this case, we are not going to find 5 derivatives or 4 derivatives and write down the series. So in fact, we're going to use the result from the previous example to come up with a series representation for Maclaurin series. Well, so we know that the cosine function, remember derivatives of power series, well, we're going to take advantage of that. Cosine is the derivative with respect x of the sine function. And well, we have a power series expansion for sine. That is, take the derivative of that. Take the derivative of x to the first over 1 factorial minus x cubed over 3 factorial plus x to the fifth over 5 factorial and minus x to the 7th over 7 factorial plus dot dot dot. That goes on forever. Just find the derivative of a polynomial, but don't simplify the denominators yet. Well, so this will be the derivative of x, of x to the first power over 1, that's simply going to be 1. And then minus 3x squared over 3 factorial and plus 5x to the fourth power over 5 factorial minus 7x to the 6th over 7 factorial plus, well, the pattern goes on forever. Well, so let's simplify this a little bit. Why not? Well, we know that 3 factorial is the same as saying 3 times 2 factorial. Is a different color. 3 times 2 factorial. 5 times 4 factorial. 7 times 6 factorial. Well, in this case, we can divide out this 3 with that 3. And this 5 with that 5, this 7 with that 7, and just cross out these factorials. That's going to leave us with the following. 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6th over 6 factorial plus. The pattern goes on forever. And in a similar way, we're going to find a power series in sigma notation for the cosine function. And well, notice the pattern, notice the powers, notice the factorials. This time we have even powers and even factorials. That's because, what do we know about the cosine function? Isn't that an even function? So this time we're talking about evenness and not oddness. So this, written in sigma notation, n equals 0 to infinity, again, it involves a negative 1 to the n power, and here the powers are null, and the powers and the factorials are no longer odd. These powers are even this time, so that's x to the 2n over 2n. However, careful with the denominator, it's the whole 2n being factorialized. And that's the answer for cosine. Instead of going through the whole process, use the information that we already have about sine, take the derivative, and that's it. For the next example that we're going to do next time, we're going to do a Taylor series and see how it's going to look like.